Okay, so this is the sixth lecture of this course. So before getting into the topics of this lecture, let me mention a correction from last lecture, that in the last lecture we are talking about if a matrix A is invertible, then its row echelon form, which we denote by A star, is identity, right. This is what so we gave two ways to we have given two different proofs in two ways. So the first proof was actually wrong, there I say not wrong, actually incomplete. So there I said that if A is invertible, then there will be a matrix B such that A B equal to identity, then reduce A to A prime, that leads to A prime B is P, where P is the product of elementary matrices, such that P A is A prime. Then I said that if the bottom row of A prime is 0, then that will give the bottom row of P is 0. Then I said that since P is invertible, this cannot happen. Actually, this is not an argument, because why for an invertible matrix this last row cannot be 0, that we need to justify. And again, to justify that, a natural way is to getting into the system of equations coming system of homogeneous equations whose coefficient matrix is that P. So that means eventually in one way or other you are always getting into the system of equations. So the second way, in which we proved A prime equal to identity in the last class, I think that is the best way. So you may simply ignore, because even this also forces us to get into that. So that is the better way. Anyway, so this is just a small correction. Let's discuss the topics of this lecture. So in the last lecture we have given the definition of a vector space. We said that we want to talk about a general algebraic structure where linear combinations can be considered. So the structure has been designed in such a way that one can consider linear combinations and see what can be, and see what further can be achieved from the linear combinations, and or in other words, to explore the properties of linear combinations in a sense. Okay, not in a sense, maybe this is loosely speaking the objective. Anyway, so what are the examples we have talked about in the last lecture for Fn, when n is some natural number, and the next example was M and the matrices, vector space of all matrices. These are the two main examples, and then we have also seen that given a system, homogeneous system, its solutions, they also forms a vector space whose additions and scalar multiplications are those adopted from Fn. This is all what we have seen in the last lecture. Okay, so before giving more different examples, let me mention a few more examples concerning matrices. The examples of interesting vector spaces of matrices. So maybe one is a space of upper triangular matrices. Upper triangular matrices. These are the matrices whose all entries below the diagonal are 0, and so this is a collection of all such matrices. The operations in this space are those adopted from so this is a subset of M. So upper triangular matrix is a square matrix. So this is as a subset of the vector space of square matrices of order n, and so the addition and scalar multiplication here is adopted from those of this bigger space. And you see, as like earlier, here also once you guarantee that given two upper triangular matrices, their sum is upper triangular, and given a upper triangular matrix, and when you multiply that by a scalar, then it remains upper triangular. Once you guarantee these two things, then actually you do not need to show the other properties which appear in the definition of a vector space, okay? Because you have established those properties for plus and dot for the whole space. So in particular, they apply for this collection also, provided they apply for this vector space also, which is contained inside that, provided you have guaranteed that given two elements from here, its sum lies here, and same for scalar multiplication. So the phenomenon that we have seen for the vector space of solutions of a given system of equations, the same thing you can see here. So similarly, lower triangular matrices, okay, and then another good collection is whose trace is 0. Trace means sum of all the elements appearing in the diagonal. So as I said, as soon as you guarantee that given two trace 0 matrix, their sum will have trace 0, and given a trace 0 matrix, when you multiply that by a scalar, it remains of trace 0. Once you guarantee that, you do not need to establish all other conditions appearing in the definition of a vector space. Since let us fix a terminology, let us give a terminology that because we are using it several times, we have used it several times already. So if happens that S is a subset of vector space, and for two elements x and y appearing in S, the x plus y, so this plus is from the vector space V, if lies in S, then we will call S as closed under addition, okay. And similarly, if given S and given alpha times alpha is a scalar, alpha times x, if it becomes if lies inside x, then we will call S is closed under scalar multiplication. So this is just for this because this phenomenon we have already noticed in three, four different examples. So and we will see this phenomenon, we will continue to see this phenomenon again and again. So therefore, for convenience, let us give them some names, so that from the next time we can refer to this phenomenon by that terminology. So in view of this terminology, you see that this is closed under addition and scalar multiplication, same for this. And once you see that there is a subset of the matrix of a subset of the space of matrices, once it is closed under addition and scalar multiplication, then you do not need to check anything, it automatically becomes a vector space, it automatically becomes a vector space, okay. So what I just said, that does not just confine you, that is not just confined for these 3 or 4 special examples, that in fact happens in generality. So let us record it as a theorem, because this appears very naturally, that suppose S is a subspace of where V is a vector space, F, the addition. So, the addition of vectors which was earlier a map from V cross V to V, and S cross S is a subset of V cross V. So, therefore, you can restrict that map to S cross S. However, that does not guarantee that image of the restriction will be S. If the image also happens to be image also happens to be contained inside S. So, then we are going to say that it is closed under addition. So, let us put that in this way. Suppose that, so assume that the image means star restricted to S cross S is a subset of S, or in other words, for 2 x y in S, x plus y lie in X, and similarly for the dot, what you have is the dot map is from F cross V to V. Now, can restrict that map to F cross S if its image lies inside S, or in other words, for every alpha in F and x in S, alpha times x is in S. Assume that one has this and this. Then what we have already seen in the 3 examples, S will become a vector space over F automatically by the operations adopted from that of V. So, at least these 3 examples has shown us that this will happen in generality, but there is a small problem. In fact, that is actually a triviality, because if these 2 properties, which as I said that we will refer from now on as closed under addition and closed under multiplication. And this will be closed under scalar multiplication. So, if a set which is closed under both scalar multiplication and addition, then we want to say that it is a vector space, or it also becomes a vector space, but as I said, there is a small problem. If you see, if S is empty, even then these 2 properties hold vacuously, but a vector space cannot be empty. So, you have to further add one more point, that the 0 vector in V also lies in S. Okay. So, we have a set containing 0 which is closed under addition and multiplication. Actually, you see, we do not need to assume 0 is that this particular 0 lies in S. You can simply assume S is non-empty. That also has the same effect. Why? Because S is non-empty means there is some V in S. Okay. Then, since this is closed under scalar multiplication, you see minus 1 times V, that also lies inside S, and V plus minus V. What is that? 1 times V plus minus 1 times V. So, 1 from the properties of vector space, 1 plus minus 1, so is 0 times V. So, what is 0 times V in a vector space? That is very easy to see. 0 can be written as 0 plus 0 times V. So, that shows 0 times V is 0 times V plus 0 times V. So, adding both sides by the minus of 0.0 times V. So, when you add this, so this becomes 0 here because of the additive inverse of that, and similarly this becomes 0. So, 0 plus 0 times v will be 0 times v. So, 0 times v will be 0. So, if you therefore, minus 1 times v is actually the additive inverse of v. Okay. So, if there is some v in S, then minus 1 times v happens to be in S, minus 1 times v is nothing but this, nothing but the additive inverse of v, that is what we have checked. Therefore, since this closed under addition, it will force 0 to be inside S. So, saying 0 lies inside S and saying anything lies inside and saying any other vector, well, saying 0 lies inside S and saying S is non-empty when S is both closed under addition and scalar multiplication. So, these are same, that is what I am telling for so long. Now, we say then S is a S, then this the restriction of plus to x and this restriction of S with respect to the restriction of the original plus and the restriction of the original dot becomes a vector space. Well, as I just want to tell you that V is a vector space with respect to plus and dot over F. We often denote this by either saying this is a vector space. I am just telling you the different ways of saying the same thing, that V is a vector space over F with respect to plus, with respect to the given addition and scalar multiplication. So, another way of saying this is we write it as a triplet and say V is a vector space over F, just a formal another way of saying that. This is just it's a formal tuple, or some people simply say that V plus dot F is a vector space. Okay, these are several ways to say the same thing. So, that is what we have seen from these examples, that if a subset is closed under addition and multiplication and also the subset is non-empty, then automatically it becomes a vector space. Okay. So, I mean the proof of this is clear. In fact, the proof of this is exactly similar to the proof of let us say when this proof for the fact that this collection is a vector space over F. Okay. Because first thing is the non-emptiness implies 0 is there, okay, and rest of the properties this simply follow from those of V. Okay. So, I mean you should notice that this is the proof of this is exactly same as the proof, the argument for the proof of this is exactly same as the argument that we have used in order to establish this collection or that collection is a vector space. Okay, so we will go ahead. So, the last example is this is also very easy to see, symmetric matrices. Symmetric matrices, that is those matrices A plus A transpose A equal to A transpose. Okay. Those matrices you can see the addition, when you add two symmetric matrices it will remain symmetric, same for scalar multiplication. So, symmetric matrices, set of all symmetric matrices will have these properties and hence it will form a vector space. Similarly, for skew symmetric matrices, let me not write that. So, symmetric, skew symmetric, and when your F is C for Hermitian and similarly for skew Hermitian, what is Hermitian? A equal to A conjugate transpose. You can see that is also closed under addition and scalar multiplication and containing the 0 vector. Here the 0 vector of this bigger space M and C, which is nothing but the null matrix. So, I have given a lot of examples of vector space concerning matrices. Now, we will move for something else. What we will do now is the following. Well, so I would like to again tell you that you should make a note of this theorem, because in many examples we will see, in many examples of vector spaces that we will see, you will observe that there is a bigger vector space containing that example, and the addition on the collection which we are talking about actually coming from the bigger vector space. Same for scalar multiplication, and the collection we are talking about is closed under both addition and scalar multiplication and naturally non-empty. Therefore, immediately we will get our collection is a vector space. So, we will see that in many of these examples which we are talking about, this this theorem will save our energy to save our energy which is to be so in principle which is to be spent on the verification of the properties, but this theorem indeed saves our energy for that, and so that we can immediately conclude that our collection is a vector space. I hope I made my point clear, that this theorem will help us a lot in the verification of the vector space properties of several examples, because we will find that there is a bigger vector space containing that, and the collection that we are talking about has these three properties. Okay. So, as I said, now my intention is to tell you the following. Okay. So, just before going ahead, so what are the main examples that we have talked about so far? So, one example was Fn. The example of solution space is actually a subset of Fn which is having these three properties. Okay. So, this something inside Fn. So, the main thing is Fn, and also for the solutions where that addition and multiplication, they are actually coming from Fn. So, Fn is the main thing, you may regard so, and similarly for the space of matrices, this is the main thing. This is in a sense the mother space from which all these are appearing from. Yeah. This is the mother space from which all these examples are appearing. Now, what we are going to see is, we will observe that these two examples, both of them are actually the special case of something. What something is, I will tell you very soon, but let me remind you that already we have observed as well that this vector space also looks exactly similar to Fmn. If you remember, in the next lecture I said that given a m by n matrix, that corresponds to a mn tuple whose first ml components will be the first components will be the entries in the first row of the matrix in their original order, and then so on and so forth. So, this space is also in a sense quite similar. Why similar? Because again, if you remember, adding two matrices here and then sending it to its corresponding tuple is same as first you send them, consider the corresponding tuples, and then you add the tuples. So I mean, though the elements of this space and that space, they look different, but you see, when the structure is concerned, as far as the structure is concerned, by structure the structure comes from addition and scalar multiplication. There you see that it is no so if even though they look different, but as far as the structure is concerned, they do not seem to be much different. So, this is what we have already observed, but I am not talking about that right now. So, I am saying that these two examples, this Fn and MNF, they are actually the special cases of something general. Okay. In fact, that will lead us to more such special cases which are interesting in different contexts. Okay, let us see. So, what do we mean by what are the elements in Fn? A typical member in Fn is a tuple, right. So, given a tuple, I can do the following. So, given a tuple, I can consider the following map. The map is from 1 up to n to f. What is the map? The map sends I to each I to xi. So, given a tuple x1 up to xn, I can consider a map sending from 1 up to n to f, sending each I to xi. Okay, fine. And then what we can do is, suppose a map is given to us. So, given a map, I can also get a tuple from that. How is that tuple formed? So, the first element of the tuple will be alpha 1, second will be alpha 2, and similarly alpha n. So, you see I have two collections. In one hand I have the collection of all tuples which is Fn. Okay. So, in one hand I have a collection of tuples which is Fn, and on the other hand I have the collection of all maps from 1 up to n to f. So, we know that from a tuple we can construct a, so given a tuple we can construct a map, and we know given a map we can construct a tuple. And it is also easy to see that these two processes are kind of they can be regarded as inverse to each other. Why? Because start with a tuple, construct the map, and then you apply the mechanism of constructing a tuple from map, that is namely this mechanism. So, when starting with the tuple you construct the map, and then applying this mechanism when you construct the tuple from the map that you have just obtained, you will get this tuple back, right. Similarly, start with a map. So, we have in a sense two different mechanisms, mechanism 1 and mechanism 2. So, start with a map, apply the second mechanism to get a tuple, and then on that tuple you apply the first mechanism and construct the map, then you will see you are arrived at the map that you have started with. So, thus these two processes are inverse to each other. Okay. So, therefore, the collection of all tuples equivalent that is Fn can be equivalently regarded as the collection of all maps from 1 up to n to f. Okay. So, this can be equivalently regarded as the collection of 1 up to all maps from 1 up to n to f. Okay. Now, we will observe the exactly similar thing for the space of matrices. How to do that? So, given a matrix, what is a matrix? It is an array of elements from F, right? Okay. So, given a matrix A, let us denote its elements are okay. So, as earlier we have elements Aij for each I and j. Remember, for each I and j I have an element. So, that shows me I can given a matrix, I can regard it, I can construct a map what is the map? Okay. So, I have a mechanism to construct a map from a given matrix. Equivalently, we will have generate a reverse process, that is, given a map, let us say if you given a map So, this is the one thing. The second thing is it is reverse process. So, given a map, if we denote this map by let us say something, let us say some f, then from that you have a mechanism to construct a matrix. How is that matrix constructed? So, the ith element the ijth entry of the matrix will be f of ij. Okay. So, from a map I can construct a matrix, and from a matrix I can construct a map. And as earlier, these two processes are inverse to each other, that is, you start with a matrix, applying this mechanism you get a map, and then on that map you apply the second mechanism and construct a matrix. For construct a matrix corresponding to that map, you will see this matrix is exactly same as the matrix we have started with, and similarly for the other one. So, likewise here also you can equivalently regard the set collection of all matrices of order m by n is same as, you can equivalently regard that collection of matrices as the collection of all maps from this Cartesian product to F. Okay. So, the main two examples that we have discussed so far, both the examples have a, though they look very different, but actually both of them has very similar pattern, that both of them can be regarded as the set of all maps from a set X. So, in the first case the set was 1 up to n, in the second case the set is the Cartesian product. So, both of them actually they have a very common pattern. Okay. So, this observation that though they look very different, one is just tuple, another is the matrices, though they look very different, at least if you do not consider very different, then somewhat different, but actually they have, there is something similar is going on for both of them. So, this motivates us to construct, this motivates us to consider the following. This is an example. So, let X be a non-empty set. So, what should be the example? As I said that I want to show that both these two are the special cases of something in general. Remember, both of them can be regarded as the collection of all maps from a set X. So, the example that we should consider now is the following, that for any given set X we will consider the set of all maps from X to F, right. This is the collection we should consider. Okay. In particular, when X is 1 up to n, this collection can be equivalently regarded as Fn, and similarly for the space of matrices. So, this is my, this set is, this is my set. So, we have a notation for that. Let us use these notations CXR. So, some authors use different notations, but let us stick to one of them. Some authors equivalently write it as F X R, so not R, F. Some author write the F X F, some author writes it by let us say L F L X F. But I mean, let us not get into that, let us just stick to one of them. So, we want to make it a vector space over F. How should I define addition and scalar multiplication? It is very easy to see, in fact, it is very natural. Well, let me put it in this way, that as I said, my question is how to make it a vector space over F. So, how to do it? The motivation for that I will get from the special cases. So, let us see first. So, given a tuple, as I said that I will not make any distinction between the tuple and the corresponding map. So, if you see here addition of two tuples x1 xn, suppose these are the tuples and their addition will be component wise. You come back here. So, what will be the map in this case? Sending each I to xi prime. When you add them, the tuple will be x1 plus x1 prime, so on and so forth, xn plus xn prime. Okay. Then what is going to be the corresponding tuple, corresponding map corresponds to this tuple? You see that is nothing but it will be just the map defined as follows, that it sends each I to xi plus xi prime. So, what you are actually doing, you have given two maps here f and g. This map is nothing but obtained by the as follows, that any given point I, the value of this map is nothing is obtained by adding the values of the maps at the given point I. Okay. So, you see the component wise addition is actually corresponds to this, which we can call this as the pointwise addition, because for any point f, so the way this addition is defined is for any given point I, you add the values of the individual functions at the given point I. Similarly, for scalar multiplication, one has this. Okay, in this example. So, this is called the pointwise scalar multiplication. Now, let us see what happens here. Here also we will have the same thing, right. If you add two matrices and then look at the corresponding map, then it is going to be the addition of the maps, corresponding to the matrices, right. So, if this matrix has component Aij, the other matrix has component Bij, then ijth component of their sum will be Aij plus Bij, and similarly the value of value of the similarly the value of the sum, well, let me rather say it more clearly. So, as I said, suppose you have two matrices A and B, from the map corresponding to A is this, the map corresponding to B is this Bij. So, the map corresponding to A plus B has the value Aij plus Bij at for any pair Ij. Okay. So, what you are doing is, again you have, so that shows that this is the map which is obtained by pointwise addition of these two maps, right. Again, pointwise addition means at any given point of time you evaluate the values of the individual functions and just add them. So, that is why it is called pointwise addition. Similarly, for scalar multiplication. So, for both these examples we see that the addition and the scalar multiplication on the space of function is actually actually the pointwise addition and pointwise scalar multiplication. So, we adopt so we will consider that in the generality. So, that now these two examples will be a special case of this. So, we define for given functions f and g, for given functions f and g, f g in Cxf f plus g to be the function from x to f, which is defined as follows: f plus g, the value of the f plus g at the given point f is obtained by adding the values of f and g at the given point x. Similarly, for scalar multiplication, alpha s is defined to be that map. So, alpha f of x is given by alpha times f of x, okay, for every x, for all x in f. All right. So, this is called the pointwise addition of functions, this is called the pointwise scalar multiplication of functions. These are motivated from the two concrete examples, from the two examples, namely Fn and space of matrices. So, now I leave this to you to check that this collection with respect to these two operations will become a vector space over F. In fact, like is very easy to see. Let us say what is the first property, associativity of the addition, that index follows from the associativity of addition in F, because over F the addition is associative. Similarly, what is the 0th element here? The constant function 0, okay. So, yeah, so and given F, its additive inverse is the function which is obtained by considering the additive negative of the value of the function, negative of the value of the function at the point at a given point x. So, things are happening. So, at the level of every point things are happening, and that influence and that causes the required things to happen, so that it is now a vector space over F. Okay. So now once we have done this for any general x, then we have actually generalized both the main examples Fn and Mnf. Okay. Now we will see some further subspaces of functions which will originate from this Cx, F. So, for again, as I said, that how we will do it, we will first consider a nice collection of functions, let us say S, the collection is non-empty and it becomes closed under the addition and scalar multiplication here. Now, by the earlier theorem, it immediately becomes a vector space over F. So, in view of this theorem, we do not have to check all the properties, that, as I said, that will save our energy a lot. Okay. So, what are the collections to be considered? Before that, let me okay. So, before getting into that, as I said that as we have already seen that both space of matrices and Fn both are special cases of this space of functions. Then I will now give another example of the space of functions, which you will recognize immediately, because that is interesting, and you have to deal with that always in any course in calculus or maybe analysis. So, we take x equals to the set of natural numbers, and let us take f equal to f is either q, r or c. Okay. Fine. So, by a map, so suppose you are given a map from n to r or c or q. So, then what you have is, if f is a map from n to r or q or c, then what you have is, so this is n, you have these members in f, right, f1, f2, f3. If you remember that, so for any for any function you are having a collection of countably many, you have a countable collection arranged in a way that you we are not you are allowed to switch any of them. So we have a collection of collection of rational numbers or reals or complex number indexed by indexed by this set of natural numbers, right. So what are such things called in calculus or analysis? This is the definition of a sequence, right. So I would like to remind you that by definition a sequence in R or C or Q is a map from N to that set, that is R or C or Q. Okay. So thus this C N F is nothing but when x is n, this is nothing but your known space of all functions, special all sequences in F, right. So this is the space of all sequences. And you should also note that, so here it is the general addition for any x, when you correspond that to this n, that will correspond to, let me just show that for you. So given a let us say a function here which we usually write in our sequence notation, right, this is how we write. So what is fn? The value of the function at the given point m. This is the notation I have for sequence. Now for two functions f and g, so what is f plus g? F plus g to the power n is nothing but f of n plus g of n, which is nothing but fn plus gn. So that corresponds to the addition of the sequences. So I am just telling it to you so that you are convinced that so your as you are familiar with the sequences and their additions and scalar multiplications. So this actually shows, indeed convinces you that this CXR when x is CXF when x is n, that indeed that is nothing but your known space of sequences. Okay. So for this function space I have, as I said, I have so I have three concrete, I have three special and important examples. One is Fn, another one is space of matrices, and space of sequences. Okay. So now we will go ahead for the next example. As I said that we will see many other vector spaces which are originating or in the sense that is contained inside this CXR in various special cases, and those examples are quite interesting and you will encounter them quite often later on, maybe in other courses, maybe in other courses, or more accurately speaking, maybe in other branches of mathematics. So what are such examples of vector spaces which are contained in or which originate from the space of functions? So one such important example is the following. That is, I will consider only those functions fx equals to 0 for all but finitely many x in x. So, this is the subset of CXR. I repeat. So, what are the collections, what are the functions we are considering here? So, given a function, I am saying that then there will be a finite set, let us say x1 up to xn, such that whenever x is not in that set, then fx is 0. So, I am considering all those functions such that for which I have a finite set in whose complement the function vanishes identically. Please do not confuse yourself with the wrong impression that this set is fixed for all the functions f. So, it is not the case that I have fixed a set and considering all the functions which vanish identically beyond that. I am not considering that. I am allowing the set to vary with the functions. Okay. So, yeah. So, the constant 0 functions lies here because it is always 0 everywhere. So, now it is easy to see that if so, as I said that since this being subset of f, subset of this vector space, in order to show this is a vector space over f, what we will do is we will check that so this collection satisfies the 3 properties in the theorem that I have discussed before. So, that we do not need to check all the properties all the properties in the definition of a vector space. Okay. So, how to do that here? So, suppose two functions f and g. For f you have a set x1 up to xn in which complement f vanishes identically. For g we have another set, let us say y1 up to im. These are all subsets of x such that g vanishes in the identical in the complement of that. Then we will consider the union of two finite sets will be finite. Therefore, in the complement of x1 up to x and y1 up to in, you see both f and g will vanish. So, therefore, f plus g x, fx plus gx, when x lies in the complement of this union, since both of them will be 0, it will be 0. So, f plus g is also having the same property. So, therefore, this collection is closed under addition. Similarly, you can show that for any given f, if x1 up to xn is the finite set, then for alpha n, alpha f, for any alpha, this finite set will also work. Okay. Therefore, this set is closed under addition scalar multiplication, and this non-empty here, hence by the theorem it will also be a vector space over f. All right. So, I will close with so this what's for this what I have just said, this happens for any x. I will give a concrete example of this C0xf for a spatial f. So, with that I will finish this lecture. So, in this example, so again let me tell you that I am now giving, so this C0f is for any x, C0xf whatever I said that holds for any x. For any xf, C0xf is a vector space and that is contained inside Cxf, and the operation C0xf is obtained from those of Cxf, namely the pointwise addition, pointwise scalar multiplication. I will now show that for some very special x, C0xf is something that you have already encountered. So these are all you see, I mean examples of vector spaces. So, yeah, let us take x to be. So, we fix a variable t, 1, t, t square, 1, t, t square and any power of all positive powers of t. Okay. Then I want to look at the functions in C0xf for this f. So, that means I will have a finite. So, if f lies in C0 xf for this x, then it means there will be a finite subset of this such that f vanishes identically beyond that. Okay. Fine. Now, we have to observe one so for any given f lying here, the choice of the finite set is actually not unique, right. You can add, let us say, so if this finite set works, then you can just add 2 more elements or finitely many elements in that set, even then it will work, because you know that as long as x is not any of this, then it will be 0. So, if an element is not any of them belonging to the bigger collection, then the same will hold. So, we know that there is a finite subset. So, there will be some powers of t. So, the powers of t which are so we can enlarge that set and assume that this set will work. I repeat, let me give you just an example. Suppose the set corresponding to this f is, let us say 1, maybe t cube, maybe t6, maybe t10. So, what I can do is I can further add t square, t4, t5, t7, t8, t9, and even I can make it up to, I can make all the powers up to t10 present in that set, and even then it will work. So, by adding more finitely many elements, by adding more elements, of course finitely many, I can assume that for any given f there exists an n such that if f is not, if such that, as I said, given f there exists n such that let me put it in this way, if let us say if I is bigger than n, then f of t to the power I is 0, right. Try to understand. This is the set beyond which I am considering f will vanish identically, okay. And we can for any given m we can always have such a set. So, this is what we will have, and this is now actually very interesting. Why so? Because for any given f we know that its values beyond, its values starting at the point t to the power n plus 1, t to the power n, all these will be 0. So, in order to know f, you just have to know the values of the function at the values of the function at till t to the power n, okay. I will just leave it in a sense somewhat incomplete to you, just to in a sense make you more curious. So, all that you need is the value of the function for all n less or equal to n. You just need to value of the function at the point t to the power n. Let us denote it by a n, okay. So, thus the function is having the value a0 at 1 and a1 at t this at t to the power n. Question: do you see any similarity? Do you see that this function actually looks like the following polynomial? in t, in the single variable t. I repeat, given a function, I have always a set such that the values, the function vanishes beyond that, and so we all need to know the values of the functions up to the point t to the power n, and when we have these values, do you think this function has some similarity with this? Vice versa, given a polynomial, can I construct a function in C0xf? These I am leaving these questions to you. We will discuss in that in the next class. So, let me just tell you, the aim is to show you that this for this particular x, C0xf is same as the space of all polynomials. So, space of all polynomials with the single variable t. Well, I will discuss that in more details in the next class. Before that, I have just given you a very brief sketch and left the rest for you to think more. Okay, with that, stop. Thank you.